Evening, you guys. Sorry it took so long to get this to you. Unbeknownst to me, I had a little more duty at home than I had expected, but all good stuff. So here, and get you up to date right now. Let me show you something cool. So there are these things called sequences and series. Sequences are just comma delimited letter or numbers in a row, kind of patterns. We've looked at those a little bit briefly a couple days ago. If you don't remember it, that's fine. But series are even more interesting because they are basically, you're going to find out that when you add up these sequence of numbers that have a particular pattern to them, sometimes they converge on a particular value. You get a certain result, or they diverge, which means they don't add up to a single value. They go on to infinity. So, or the other option we actually will run into is oscillating, something like with the trig function. But here you have some convergent examples. Here's a nice geometric representation of what it looks like. These are awesome. I mean, just look at these for a second. You'll get an idea of what we're talking about. First one on the top is a 1x1 block. Take a look at how you can create that 1x1 block. It's the basic premise that what if I keep taking a half of the pieces remaining? Take a half of the whole block, add another half of that remaining half, and a half of that remaining half, and a half of that remaining half, and a half of that remaining half. The same concept as you probably heard before is there's a mathematician, was it Neo or something like that, I forget his name, but anyway, he said that, proposed that if you walked, only went halfway, completed or only consumed a half of something, every single time one person consumed a half, another person consumed a half, another person consumed a half, well, you'd never actually take the whole thing because you'd always just take half, a portion of it. Well, this is that same idea, but take a look at this. It's kind of fun, isn't it? So now let me just add it up. Okay, so we have 4th, 8th, 16th, 132nd plus 164th. Well, if you keep adding up all those pieces, like put them all together, you can see you get a resultant value. We're going to get 1. We're going to get this area of 1. Half of the area plus another half of that remaining area plus another half of that remaining area. And if you keep going, we are going to get the whole box. So we know that this converges to 1. The idea is that, yes, there is a resultant value that you get from it. It's a nice pictorial representation. The one on the bottom, same idea. This one's different. If I have 3 1/4 pieces, leave the remaining internal 1/4 piece and break it up into 3/4. Again, usually 3 of them, so 3/4 plus 3/16 plus 3/64, and you keep that pattern going. It just concentrically moves toward the center, but we are going to get the single 1 unit of that triangle. We'll talk about what that converges to in a little bit, but the idea is you can see it go somewhere. Well, there's some notation issues we should address here. The common factor that goes between one term to the next, and so if I take, let's see, I got the right color, yep. If I go from 1/2 to 1/4 or 1/4 to 1/8, the common factor is 1/2. So that's important. We talk about this as being 1/2. There's a factor in there. So this sum piece this is an index. N equals 1 is the beginning of where you're going to start your counting process, and then the upper portion, the infinity, is where you're going to end. So what we're going to do is sum up 1/2 to the nth power. That means we're going to put in whatever n is equal to at the moment. So it starts n equals 1, get 1/2. Then you do n equals 2, get 1/4, n equals 3, n equals 4, n equals 5, and so on. Adding those together, that's what the summation notation tells you, is how to add them together. And what you'll get, this little symbolic notation, is a shorthand for that big long summation we have up at top. Okay, let's keep on rolling. Down below, same idea. The 1/4, 1/16, or the 3/4, 3/16, 3/64. The 3 is constant, so I pulled that out front. What's variable, though, is that 1/4 to the n power. It's 1/4 to the first is what gives us the denominator 4. 1/4 to the second gives us this denominator 16. 1/4 to the third gives you that 64th. And what we're doing, a summation symbol indicates we're going to add those up to infinity. And what we have is that they do actually end up in a singular value, a singular area. So this is really similar to what we did before. There's something about this infinite summation, like when we do integrals, those are infinite summations. Even in a situation when it looks like it's going off into infinity, we in fact get a fixed value for the area it occupies. So here's another thing we should take a look at. There is something that hopefully we have a chance to prove more in class, maybe a good additional problem for you guys to tackle. But a over 1 minus r is what a geometric series converges to if the geometric series is in fact convergent. Now we'll talk about what makes it convergent here in a little bit. There are characteristics that have to happen. You might even already have some intuition about it. The fact that this r value, the growth rate, is something smaller than 1 makes it grow, or makes it converge on a value. We've already had a little experience with that. Same thing down here. The fact that this growth rate is something smaller than 1 is part of the reason why it converges. But let's continue on. If I actually do that calculation on the top function, we'll find out that it converges to 1, which we can see it's a box. It's 1 by 1. But the formula says if I have a, where a is the initial amount, over 1 minus r, where r is the growth rate, then what I can look at, the initial amount, be careful. Initial amount means when you put the first indice in, n equals 1, into the function, what do you get out first? So you get out 1/2. So 1/2 is a over 1 minus r, which is the growth rate, which happens to also be 1/2. So if you put that together, you get 1 over 1/2, which is 1. So that's what it converges to. That's the story. That's the general idea of this geometric series. Geometric series are a particularly interesting one because they do converge. They have the potential to converge. There's only one other type of series that has that potential. It's called a telescoping series. The rest of them, they don't necessarily, we don't get to say they converge to this value, 1 or 5 or 7 or anything like that. But we can just merely say they converge or diverge in general. Sometimes we can't be very specific about it. So that's what makes geometric series really cool. All right, I have an assignment coming out for you guys to take a peek at. There are going to be some geometric series, and I want you to take a look at what you can do with those. Enjoy.